Yeah, first I would like to thank the organizers for inviting me to this great place. I enjoy it every time I'm here. And well, and also for giving me the opportunity to speak on this conference. So, well, the title is Analytic Torsion for locally symmetric spaces of finite volume. Well, the analytic torsion is a spectral invariant of a compact Riemannian manifold, which was introduced quite some years ago by Ray and Singer as the analytic counterpart of a topological invariant called Renormalized torsion. So the main, well, in between, it has had applications in many different fields, in particular also the so-called holomorphic torsion. Well, but the main purpose of this talk is to define and study, or let's say the main purpose of the project I'm presenting here is to define analytic torsion and study it for a certain class of non-compact manifolds, namely the locally symmetric spaces. Well, locally symmetric spaces are not stratified, but well, if you can, initially they are not stratified, but they have a very natural compactification as a manifold with corners, and as such, this manifold with corners is stratified, so it's justified to talk about this in this conference. And the compactification has important impact on the spectral theory of the corresponding Laplace operators. To begin with, let me briefly recall the definition. So, the setup is as follows. We consider a compact or oriented Riemannian manifold, dimension is n, and a representation of its fundamental group, which I, for simplicity, will denote just by gamma. So this is the fundamental group of our manifold, and we consider a finite dimensional representation of the fundamental group on a real or complex vector space. Then this representation has associated, or there's the associated flat bundle so we pick a Hermitian metric in this flat bundle, and then we can talk about the Laplace operator on p-forms with values in this flat bundle. So as we know, this operator has discrete spectrum consisting of a sequence of eigenvalues. We form the corresponding zeta function which converges in this half-plane real part s bigger than n over 2, admits a meromorphic extension to the entire complex plane, which is holomorphic at the origin, and then you define the so-called regularized determinant of this operator by the following formula. So, exponential minus derivative of this function, zeta function, at the origin. Okay, so this is the regularized determinant, and then the analytic torsion is a weighted product of such determinants. The product runs from 1 to n. So, of course, if you're not familiar with this, you may ask, why do we consider this kind of product? Well, it's inspired by the topological invariant, which was, so to speak, the starting point for these considerations. And this is to define it exactly in this way. This is the Ray-Singer analytic torsion. Well, there is a topological counterpart, but I think you will hear about this in the next talk. So I don't say anything about this, except one thing which I want to emphasize here, which is the basis of some interesting application. Or this is the relation with cohomology. So assume that the flat bundle has an underlying integer structure. This means we assume that there exists a lattice in the corresponding representation space, which is gamma invariant, so preserved by the action of gamma. And if this is the case, then we can talk about the associated local system. So this is a local system of 3 set modules of finite rank. And well, with this local system, we can also talk about the cohomology of X with coefficients in the local system. So this is a finitely generated abelian group, and so it has a free part and the torsion part. And using this, we define, first of all, using the free part, we define the so-called regulator. Well, the free part of the cohomology is a lattice in the real cohomology, and we can talk about its volume. So this is the real cohomology, and free part of the integer cohomology is a lattice. So, and here, of course, this is with respect to the Hutch isomorphism. So we use the inner product induced by the harmonic forms. Well, this is the co-volume of the free lattice, and then we consider the alternating product. Well, this is called the regulator. Well, also. And then we have the following theorem, which in a sense is due to Giga and myself, well, which is a consequence of some more general result. It says, under these circumstances, the spectral invariant is equal to the regulator times the alternating product of the order of the torsion groups. So that's, of course, looks like some interesting equality, because on the one hand you have this invariant constructed in terms of the spectrum of the Laplace operators, and on the other side you have a pure topological invariant. And in particular, this gives you and provides you with an analytic tool to study torsion in the cohomology. And well, if you combined, okay, yes, well, it gives you an analytic tool, yes. And just one more thing which I want to mention. This is there's also a so-called L2 invariant, the L2 torsion, which was introduced by Lott and Matthei. Well, the basic for the definition is the theta function can be expressed by Mellin transform in terms of the trace of the heat operator. So this is the corresponding dimension of the space of harmonic forms. And then you pass to the universal covering. Choose a fundamental domain. So a fundamental domain, and then we consider the kernel of the heat operator on the universal covering. So we lift our Laplace operator to the universal covering. So this is the heat operator on the universal covering, and we take the kernel. And then you define the gamma trace or the von Neumann trace of this operator. Well, it's only of interest if the manifold is non-compact, if the universal covering is non-compact. So this is, you restrict this kernel to the diagonal, takes the pointwise trace, and integrates the thing over the fundamental domain. So this is the gamma trace, and to define this torsion invariant, you just replace the trace of the usual heat operator by the gamma trace. Of course, in order to be able to do this, you have to verify a number of things. Well, to make sure that the integral is defined and admits a meromorphic extension, we need to know that the gamma trace, first of all, for small t, has an asymptotic expansion, as we know that this is the case in the compact case. Well, this is no problem, but the real problem is for t going to infinity. You also have to know that if you subtract off the corresponding, well, if t goes to infinity, it approaches the so-called L2 Betti number. And then you have to know that the difference decays at least as a power of t. This is not always known, but if this is the case, then you can define the L2 torsion in exactly the same way as it was defined in the compact case. And okay, so now I also have to recall some other thing. This is called L2 approximation. Or approximation of L2 invariance. So this is a subject which has mainly been pursued by Luc. Well, there's his well-known book about L2 invariance, and this is one issue. So let's go back to the case of a compact manifold. So we have X, the fundamental group. And now assume that there is a tower of subgroups. So descending tower of subgroups of normal subgroups of finite index. Intersecting in the identity. Then, well, you consider the corresponding covering spaces. So this is still a compact space covering our initial manifold. And then a legitimate question is, if you have any, well, standard invariant like Betti numbers or the index or anything else, and you consider the corresponding object on the universal covering, can it be approximated by these invariants of the finite coverings? Well, a sample of such a result is a theorem by Luc. It was initiated, the problem was raised by Kashtan in the context of algebraic manifolds. So it says if we are in this situation, we have this kind of tower of subgroups and so on. And we consider, take the Betti number of the Chase covering space, renormalize this by dividing by the degree of the covering. Then this has a limit if J goes to infinity, and this is the L2 Betti number of X. Well, the L2 Betti number is just the limit, so take this gamma trace and the limit if t goes to infinity. Awesome. This is just the usual. So this is the L2 Betti number in this case. Well, this is a sample of a theorem which approximates, so to speak, the L2 Betti number by the renormalized Betti numbers of the finite coverings. There's, of course, another well-known theorem which most of you may know. This is the gamma index theorem of Artia, which a more sophisticated question is, this is a conjecture. So you may, instead of considering so you may now consider a more sophisticated spectral invariant, not only the zero eigenvalue, namely the question is, if you are in the same situation, we have a tower of normal subgroups and so on, takes the logarithm, the analytic torsion, renormalized, and then, of course, it may not always be, the right-hand side may not always be well defined, but in case where you know that the L2 torsion is defined, then you would conjecture that it can also be approximated by the corresponding spectral invariance of the finite covering. So this is a conjecture of Luc, and it's still widely open. Okay, this is, well, if you consider, so if you know this conjecture, then combined with this theorem, it finally gives you something about so it tells you something about the growth of torsion in the cohomology. So for example, suppose that the real cohomology vanishes and the regulator is just one, then the only thing we have on the right-hand side is the alternating product of the torsion groups, and then combined with this conjecture, it gives you a similar result, for example, for the growth of the order of the torsion groups. So now we come to this class of manifolds which I want to consider, namely locally symmetric spaces. So the basic setup is we consider a semi-simple Lie group, real Lie group, well, with some additional assumptions like non-compact type. And then we fix a maximal compact subgroup. So this gives, and the corresponding Riemann symmetric space, G mod K, equipped with the invariant metric, G invariant metric. And then we also fix a lattice in G, meaning a discrete subgroup of finite covolume. And well, for the purpose of this talk, I will assume that it's also torsion-free. So it has no elements of finite order. So this is the basic setup. And then we can take the quotient of the symmetric space by the action of this discrete group. It acts freely under this assumption, and we end up with a manifold, Riemannian manifold, a locally symmetric manifold of finite volume. So this will be now the basic manifold we want to consider. And in addition, well, the basic example which you can keep in mind all the time is that the symmetric space is just a space of symmetric positive definite matrices of determinant 1. And gamma is a subgroup of finite index in SL and Z. So this is, for example, one of the basic examples. So, well, to state the result, which, or one of the results in this context, I have to introduce some invariant. This is the fundamental rank, which means we consider the complex rank of G, by which I mean I take the Lie algebra, complexify it, and take the rank of the complexified real algebra, minus the complex rank of K. So this is the so-called fundamental rank. And, well, we also consider a finite dimensional representation of our Lie group G. Huh? No, an arbitrary finite dimensional. Well, G is non-compact, so it has very little unitary representations. It's finite. It has very little finite dimensional unitary representations. So, yeah, complex or real, and then we can restrict this to our subgroup gamma, and in this way we get, for each of the such representation, we get a representation of gamma. Somehow it's blocked. Okay, and so for the moment, I still assume that this quotient is compact, so I'm assuming that gamma is a co-compact lattice in G. I just want to describe one of the results which is known in this context. Well, motivated by considerations about Galois groups or representations of Galois groups, Bergeron and Rencontres studied, for example, this conjecture in the context of locally symmetric spaces. And, well, to state the result, we have to restrict, or we have to impose some additional condition on rho. Well, so we have all these, so this is our lattice, and we have the descending chain of normal subgroups of finite index and the corresponding covering spaces. And now this representation is called strongly acyclic. If all the Laplace operators which we consider have a uniform spectral gap, meaning the spectrum, so we consider Laplace operator on P forms on the corresponding covering space twisted by the corresponding flat bundle coming from our representation rho. And the assumption is the spectrum has a uniform lower bound by C. So, of course, this is a rather strong assumption. And, well, of course, the question is, do such representation exist? And, well, the answer is yes, they do. But it depends on, so it's possible to show that you can always find such representations. And then we have the following result of Bergeron and Rencontres. So we are in this setup. X is compact. Have this tower of subgroups. And rho is strongly acyclic. Then it's indeed true that so if you take the logarithm of this analytic torsion renormalized by or divided by the degree of the covering, then this is indeed has indeed a limit, and the limit well, this is in this case the L2 torsion. It's simply because the Yeat kernel is, so to speak, invariant under G on the universal covering. It has a very simple form. It's the volume of the manifold times a constant which is independent of gamma. And, well, in fact, this constant can be computed explicitly using the Blancharel formula. So it turns out that this constant is non-zero if and only if the fundamental rank is equal to 1. So the simple groups which have these properties are the orthogonal groups SPQ, P times Q art, and SL3. Well, if you have this result and combine it with the other result about expressing this, so if in addition to that, there is an underlying integer structure, then you can replace this by the order of the alternating sum of the order of the cohomology groups, the torsion in the cohomology groups, and you get some result about the growth of torsion in cohomology groups. So just let me briefly indicate, I cannot say much about the proof, but I just want to briefly indicate where this assumption about the uniform spectral gap comes into play. Well, you start out with the formula which I mentioned already, which expresses the zeta function in terms of the trace of the heat operator. And so, well, we have to study behavior of determinants, and this can be expressed through the trace of the heat operator in the following way. Well, under the assumption that the representation is strongly acyclic, there's no real cohomology, the harmonic forms vanish. So we can write it in this way. Well, under this assumption, it's exponentially decreasing if t goes to infinity, so this is well defined. And of course, at s equals 0, we have to define it by analytic continuation. Now you choose some a, some positive a, and you decompose the integral in this way. And now it's not difficult to see that the existence of this uniform spectral gap, then of course here we have to, okay, then this implies that, well, first of all, if we decompose the integral in this way and compute the derivative at s equals 0, then the second part, this integral is defined for all s, and the derivative is at s equals 0 is just this one. So here we have the corresponding Laplace operator on the covering space. So this is the contribution of this integral to the derivative. And under the assumptions that we have this uniform spectral gap, then one actually can show 1 over the volume is less than, so if we pick any epsilon, then for a sufficiently large, we can make it smaller than epsilon for all p and j. So this is one of the ingredients, or this is where this assumption enters in the proof, and then to deal with the other part, you have to use the Seibach trace formula, which is a little bit longer to explain. What? It just comes from, well, you have this estimation, so it's less than, so C is the unit. Yes, and then, of course, you have the trace at t equals 1. And you still need to estimate this, so it involves, of course, the volume, yes. But this is how you prove this, yes? And, of course, it's very interesting to see what happens if the representation is not strongly acyclic. Well, then the problem is, so the general case, so let's say rho is not strongly acyclic. Then the problem is that eigenvalues may cluster near 0. And, well, in fact, you can prove that they will cluster. So, for example, if we consider a hyperbolic 3 manifold, then it's fine for the Laplacian on functions and on 3 forms if you work with an arithmetic group, then you can prove for functions and 3-form there is still a spectral gap. Well, there is the eigenvalue 0, but then there is a uniform spectral gap if you consider appropriate sequences. However, the trouble comes with delta 1. For example, just take the trivial representation. Then for delta 1 and delta 2, you will have, because the continuous spectrum of the Laplacian on the hyperbolic 3 space consists of the whole half-line, and so to speak, the spectral, normalized spectral measure for these Laplacians on the covering approximate the measure on the Blancharel measure on the universal covering. So what happens is that eigenvalues, if you move up in the tower, eigenvalues will cluster near 0. Well, this is of course a serious problem. You cannot use this approach. But the problem is to understand in what way the eigenvalues cluster. If they would cluster in a very equidistributed way, then it's still fine, so you can prove a convergence. But at the moment, this is very different, very complicated to understand. I mean, an example, if you wish to understand this, you just take the n-fold covering of the circle, then you can write down the eigenvalues explicitly by the length or the covering. And then you see that the eigenvalues cluster, but they are very equidistributed. And using this, you can show that in this case, everything is fine. So this is the situation, or this is a very interesting problem. And at the moment, it's not, no one has a substantial idea how to handle this problem. Okay, now there's so much about the compact case. Now I'm coming to the non-compact case. So there are, as we have seen, or if I try to emphasize, the study of these problems has interesting applications to the cohomology of groups, and therefore one would like to know if this can be also, this method can be also developed in the non-compact case, because, well, many interesting discrete groups like SLNZ in SLN3 is non-co-compact, so it's not co-compact. And so the question is, can we extend this method to the non-co-compact case? So now I assume, so this will be 3, the finite volume case. So again, X is a locally symmetric space, but non-compact anymore. Well, there are two. The first case is, for example, a hyperbolic 3 manifold. So we write H3 as the quotient of SL2C by SU2. And then a discrete group would be, for example, SL2 with coefficients, the Gaussian integers. So this would be a lattice, or this is a lattice in SL2C, a discrete subgroup of finite volume. Okay, and the other case would be SLN, which I mentioned several times. So the first problem we are facing is the Laplace operators under this assumption. And well, for most of the representations, there may be representations where the spectrum is discrete, but in general has continuous spectrum. And the first question is, so the regularized determinant is not defined because its definition uses the eigenvalues and the discreteness of the spectrum, and in this case this does not work, or the heat operator has no trace, is not trace class, and we cannot use this definition of the determinant. So, and then the problem is, well, if it's not defined, so it comes down to define a renormalized version of the trace of the heat operator. Well, need to renormalize trace of the heat operator. Well, and in a different context, this has been also used or done in other cases. So we follow Richard Melrose. We followed Richard, what he did, or in the case of manifolds with cylindrical ends. So you simply, so you approach this problem how, in the same way as a good physicist would approach it, or what physicists also do all the time if they want to renormalize something. If it's not converging, then we make it convergent. They just subtract off the divergent parts. So renormalization is a big issue in physics, and this is the same approach which is used in this context. Well, it's relatively easy for a hyperbolic manifold because this is a manifold with cos, and well, it has now been used by various authors. I mean, for example, Pierre Albin and Frédéric Auchan in their work, which will be, of course, discussed in the next talk. They use exactly the same approach. So the manifold, well, if you talk about a hyperbolic manifold of finite volume, then it's a manifold with cos. So it has a compact part and some ends. So this is just, in this case, it's a torus of dimension n-1 cross a half line, of course equipped with a hyperbolic metric. And then what you do is just, you truncate the manifold by cutting off the cos at a certain level. So take T sufficiently large and truncate the manifold. So this is the truncated manifold at level T. And now you take the kernel of our heat operator, and well, this is a manifold, compact manifold with boundaries, so in any case we can take the pointwise trace of the kernel, integrate over the compact manifold, and then the main issue is to show that if t goes to infinity, there is a kind of asymptotic expansion. There is, well, it looks like this. So of course it diverges like log t, then there is a constant term, and there's something which goes to 0. And you just renormalize the trace by taking the constant term. Well, this, of course, to show that there is such an expansion, this requires some work. But anyway, this exists, and then you define the regularized trace of the heat operator to be the constant term in this expansion. Okay. Well, there's another, of course, another way to renormalize this. Well, instead of truncating the manifold, I mean, here this is slightly different from the manifold, from the case of manifolds with cylindrical ends. Well, of course, this is what I describe here, is what Richard used in this context. Here we have the cusp, and the trouble, the only part that makes the trouble is the constant Fourier coefficient. So you take your heat kernel, for example, on function, expand it on the cusp in the Fourier series with respect to the modes on the torus, and then all the Fourier coefficients, non-zero Fourier coefficients, are square integrable. So the only trouble is the zero Fourier coefficient. And you can also, instead of truncating the manifold, you can truncate the heat kernel. Let's say by chopping off the zero, or subtracting off the zero Fourier coefficient at level t on every cusp, and then integrate this over the whole manifold. And then the interesting thing is that this is in fact a polynomial in log t. So there's no remainder term. This is a true polynomial. Okay, and now the important thing, so this is now the renormalized trace, which you use in the same way as in the compact case to define the determinant and the analytic torsion. Of course, in order to be able to define it, you need to know a number of properties. Like the first thing, what you need to know is the behavior if t goes to 0 and t goes to infinity. And, well, but the first observation is that this approach, the second one which I described here, namely truncate the kernel and integrate it over the manifold, this is exactly the approach which you use to prove the Hilbert trace formula in this context. And so it's not surprising that we have the following result. So the regularized trace of this heat kernel, this is the spectral side of the trace formula. This means, first of all, there's the standard contribution coming from the eigenvalues. So the operator has discrete spectrum consisting of a sequence of eigenvalues, and it has continuous spectrum. And the contribution of the continuous spectrum, or the main part looks essentially like follows, as follows. And then it's the usual thing, the logarithmic derivative of the, so ds, so we have a scattering, so there's scattering theory, we have a scattering matrix. C is the corresponding scattering matrix, and we take, so to speak, the logarithmic derivative, the trace of the logarithmic derivative. And then there are some minor terms. So this is the spectral side of the trace formula, which means you collect all terms coming from the spectrum on one side. And this is, of course, the basis to study the regularized trace. Its behavior for t going to 0 and t going to infinity. So for t going to 0, there are several approaches. Well, you can use the B calculus to study its behavior if t goes to 0. This is, of course, the method used by Pierre and Frédéric and so on. This is one possibility. And the other one is, in this context, we would use the trace formula. And let me briefly, the Hilbert trace formula. So this is the approach which, also I forgot to say, this is now joint work with Jonathan Pfaff, what I'm describing now. Well, how do you use the trace formula? Well, the trace formula is an inequality of two distributions, so to speak. On the one hand, on the one side, we collect all the terms coming from the spectrum, from the discrete and the continuous spectrum. And on the other side, we have, so to speak, geometric terms. So if you apply the Selberg trace formula, then it means, so I need some preparation. If we consider this operator, this is the corresponding heat operator on the universal covering on hyperbolic space. And, well, it commutes with the action of the group. And so it's a convolution operator. And therefore, it has a kernel, so given by a convolution kernel, this is just a map. So I delete the various indices, I just call it HT. So this is a map or smooth function defined on the V group with values in the following thing. So this is a representation space, and P is just in the orthogonal complement of K. So this is the Cardan decomposition. And yeah, and the corresponding representation, and it behaves on a right and left multiplication by K according to the representations. And then we take the local trace. HT of G is just the trace in the endomorphisms of this kernel. So this is a smooth function, and it's not compactly supported, but it belongs to the space of rapidly decreasing functions on G in the sense of Harishchandra. So this is Harishchandra's Schwartz space. And then the trace formula, if you apply the trace formula, this tells us that the regularized trace, so this is the sum. Well, in principle, you take this truncated kernel, integrate over X, and then you decompose your group into conjugacy classes, and every conjugacy class makes a certain contribution to this. This is the right-hand side. So there are various terms, which I will not all describe in detail. So the first one is very simple. So H1 I is just the contribution of the identity. This is the volume of X times the heat kernel or the trace of the heat kernel evaluated at the unit element. Then H, this is the contribution of the hyperbolic conjugacy classes. Well, they don't make any trouble. This term is exponentially decreasing if t goes to 0. Well, it can be expressed in terms of the lengths of closed geodesics associated to the conjugacy classes. The interesting terms are the last two ones, which correspond to the parabolic conjugacy classes. So T1 of HT is of, so we have the Iwasawa decomposition. So N is unipotent group. Its Lie algebra is just isomorphic to, well, now I call this better D. So we are working on HT modulo gamma. So this is just RD minus 1. And then the first distribution, this is a constant depending on gamma times the following integral. So this is just this integral. And well, this integral can also be analyzed very easily because it's an invariant integral. It's the behavior in t if t goes to 0. The other term is also a constant depending on gamma times an integral which is independent of gamma. But in addition to that, we have some weight factor, and this is the following factor. So log means just the identification of n with its Lie algebra. So the difficult part is this one. But while using, so to speak, standard construction of heat kernels and so on the corresponding symmetric space, it comes down that you need to study the following kind of integral. So this is, well, we identify this group, the unipotent group with RD minus 1. And then we have, so to speak, the leading term in the heat kernel. This is the geodesic, D is the geodesic distance. Okay, there is a, so then I better call it rho now. Rho is also not good. So this is now the geodesic distance on the hyperbolic space. Or call it n first. So x0 is the base point, the coset of the identity, and divided by 4t. And then we have this log n. So now this integral can be, well, you just transfer it in an integral in Rn. You have to compute the geodesic distance, how it is expressed if you identify this with RT minus 1. And then you can easily, well, you use, so to speak, stationary phase approximation to treat this integral. And the result, the final result is that we indeed have an asymptotic expansion. So the trace, the regularized trace behaves like this. So there is T and then there is another contribution which contains logarithmic terms. So there is minus t minus 1 over 2 plus j over 2 times the logarithm. Also that, well, this is a double sum. So, well, there are logarithmic terms appearing in this asymptotic expansion. In fact, well, this is maybe not true. There is only one power of log. I'm sorry. I'm thinking about the more general case. So, and the log term comes exactly from this kind of integral. And, well, you can also study the large time behavior using the expression. Well, and now you are in good shape. Of course, the same result can be deduced by using the B calculus. The only difference is that, well, for the problem which I described at the very beginning, behavior in towers, so if you take the logarithm, divide by the degree, and you consider the sequence, then you have to get hold of these constants. And, well, they are not so easy to control. They are, so to speak, well, the cusp is a torus given by a lattice. And the lattice in RD has an associated Epstein zeta function. And, well, this Epstein zeta function at the origin, if you renormalize it, has a pole And this is the constant term, and this is the residue in the Laurent expansion. And then you have to control these residues in constant terms. And now if you move in a tower, it could happen that the tori, which are the cross sections of the cusp, become very long and thin, which means in the corresponding moduli space of tori, SLN R modulo SON, they converge to infinity. And this has to be, this would, so to speak, damage the approach. You have to make sure that the tori all stay in a compact set of the corresponding moduli space. So, and this can be proved for arithmetic groups. Okay, so the final result is that if you have, for example, in the SL3 case, in the case of hyperbolic manifold, like the group, any group like this, and a tower of congruent subgroups, then we have the convergence result, which we know in the compact case. And now the real ongoing work is to extend this method to the higher rank case like SLN. But now my time is up and I cannot tell you anything about this. Okay.
For short questions, so we have a microphone because it's registered, so if you have some.
You have really terms t to the j over 2 log t, not only integer contributions?
Okay, say again. We have?
In the last term, there's the log terms.
Yes.
Don't they just come with integer t powers, or with full half integer t powers?
I think so. You mean there's, of course...
This fact is clear, yeah.
And it's probably integer powers, yes, I think so. Mm-hmm.
Other question? No. So if there is no question, see you again.
Okay.